We're going to look at 4 different algebraic tricks that are very useful for computing limits. So we're going to investigate these 4 particular limits, and there's going to be a different algebraic trick for each of them. Let's start off with something pretty easy. Let's just do good old factoring. When I look at this particular limit, the first thing I might think is, well, hold on, do I need to do any algebraic tricks at all? Well, what happens if I take this value of -2 and actually plug it into the limit? Well, if you just evaluate the top and the bottom at the value of -2, you're going to get 0 divided by 0. You're going to get an indeterminate form. So we have to do some algebraic trick. I have to do something to just not have a 0 divided by 0. So the first thing I notice when I look at it is I've got x's everywhere. So why don't I just factor out an x from the top and factor out an x from the bottom, and that's going to leave something like this. And I can cancel those x's, but I still have a quadratic that is still 0 on the top and it's still 0 on the bottom. So I have to go a little bit further. The quadratic, the x squared minus x minus 6, I can factor that as being the limit as x goes to -2 of x plus 2 times x minus 3 on the top, and another copy of x plus 2 on the bottom, as in factoring the quadratic to get a product of 2 linear terms. Well, now when I look at it, it's way nicer because I got an x plus 2 on the top, I've got an x plus 2 on the bottom, I can cancel those, and what I'm then left with is just the limit of x minus 3. Now, all the way along here, I never plugged in the x equal to -2 because it would give me a 0 over 0, but now I've canceled enough that I can plug in the value of -2. There is no longer a 0 divided by 0 scenario, and so I can just plug it in and get -5. Now, just a couple points about notation. Notice that I have an equal sign in front of every single one of these limits. That's an unbroken chain of equalities. And notice that I have a limit sign in front of every single one of them until that final step where I plug in the value of -2, and I'm not allowed to plug in the -2 earlier because it would just be 0 over 0. It would be an indeterminate form. All right, factoring was our first example. Let's look at the next one. This one is expanding. It's sort of the opposite of factoring in some sense. I have the quadratic here written as x minus 2 squared. Let's go and expand that out. Let's write it as x minus 2 times an x minus 2. Well, if I multiply that out on the numerator, I'm going to get x squared minus 4x plus 4, then subtract off the 4 I already had on the top and haven't changed the denominator. Now, the reason this is nice here is that in this example, the plus 4 and the minus 4 cancel, so those can go away. Well, I'm still not done, because even if I get rid of the plus 4 minus 4 part, I still can't plug in 0 yet, because it's going to be a 0 over 0. It's going to be, once again, indeterminate. So what can I do? It's the same trick we just saw when we looked at factoring. There's lots of x's around, let's factor out an x. So if I factor out an x and cancel it, then I've got just x minus 4 remaining with an x on the top and bottom. We get rid of those, it's just the x minus 4, and finally, I can evaluate the limit, I can plug in the 0, and I get -4. So again, another unbroken chain of equalities with a limit in front of every single one of the expressions, except the last one where I finally go and evaluate the limit. So factoring and expanding, though, were kind of similar, but now let's go and look at common denominators, which is quite a bit of a different trick. So in this example, I have the difference of 2 different things, a difference of 2 fractions. Each of the fractions is individually problematic. So for example, the limit as x goes to 0 with just 1 over x by itself does not exist. So whenever you have a difference of 2 of these things where they both do not exist or they're going to be infinite, this means we have to do something else. And when it's written in fraction form, a common denominator is a useful trick. So what I do is I multiply both sides by the other denominator and I put them all together. The general formula for finding this denominator is if you've got a over b plus c over d, then you can put them together as ad plus bc over bd. It's cross multiplication. Now, I've got this. Let's see whether it's actually any nicer for us. Well, indeed, notice I've got a plus 2x and a minus 2x. I can cancel those. Okay, so if we cancel those, I'm just left with a bunch of x squareds on the top and x cubed plus 2x on the bottom. Not bad. But again, I cannot plug in x equal to 0. Again, it's indeterminate. Again, it's 0 divided by 0. I have to go back to my first algebraic trick of factoring. So let's factor out, well, it's x squared on the top, so how about we factor out an x squared? Certainly there's an x squared in all of the terms on the denominator, x squared or higher. So if I factor out the x squared, I'm just going to get a 1 on the top and an x plus 2 on the bottom. Now it's not 0 divided by 0, so now I can plug it in, and I just get the value of a half. Alright, we're doing pretty good here. That's 3 tricks down. Time for the 4th. This is called the radical conjugate. And the radical conjugate applies in scenarios where you've got this either a plus or minus, but with a square root in it. Note that if I just plug in the value of 4, it would be 0 on the top and 0 on the bottom, so I have to do something. And what I'm going to do is I'm going to multiply by just 1. But not just 1, a very fancy version of 1, a very specific version of 1. You see how it's square root x minus 2? I'm going to multiply the top and the bottom by square root x plus 2. And because it's the top and the bottom, this is just multiplication by 1. It's totally fine. In general, if you're going to have a square root a plus or minus the square root of b, you multiply by square root a and then you reverse the sign. I call it minus plus. So square root a minus plus square root b divided by square root a minus plus square root b. But multiplied by a fancy version of 1. Now, why is this so nice? It's because if I take the numerator here and I go and try to multiply it out, the cross terms cancel. In other words, I get the square root x and the square root x, they become an x. The minus 2 and the plus 2 becomes a minus 4. But the other terms, the minus 2 square root x and the plus 2 square root x, they cancel. So all I'm left with in the numerator is just x minus 4. See how nice radical conjugates are? They take this messy thing with square roots and they make it really simple, at least on the top. The bottom's kind of messy, I've mashed that together, but it's going to turn out to be messy in a way that's okay because I can just plug the values in. Well, not yet, I suppose. Again, I cannot plug in 4 because it's 0 divided by 0, but I can cancel the x minus 4 on the top and the x minus 4 on the bottom. That's perfectly allowed. So if I cancel the x minus 4 on the top and the x minus 4 on the bottom, then I'm just left with the 1 over square root x plus 2, plug in the value of 4, and I get a quarter. Alright, so those are 4 algebraic tricks that hopefully are going to help you when you're computing algebraic limits, but we also use them all the time in calculus. You're going to use them a whole bunch as you go forward, and they're just little algebraic ways to make your expressions nicer.